Hello dear student, this is Professor Ashok Kumar. I welcome all of you. Today we are going to discuss chapter number 5, that is gears, and this will be the part 2 on same chapter gears. During my previous video lecture on same chapter part 1, I have discussed about an introduction of gears, types of various types of gears, that means spur gear, helical gear, bevel gear, spiral gear, rack and pinion, and of course worm and worm wheel. Then after we have also covered different types of gear train, that means simple gear train, compound gear train, reverted, and at the end we have also discussed on an epicyclic gear train. So today in this video lecture I will discuss remaining portion of chapter number 5, that is gears. First topic that we are going to discuss, it is very important as far as your exam point of view, and that is the law of gear. Generally, law of gear relates with two gear or teeth of the gear, in which specially there is some geometric relation, and that relation is highlighted by the law of gearing. To understand closely about law of gearing, let's consider the portion of two gear teeth which are in mesh, and let two teeth are in contact at point K. So, and the teeth, that teeth are rotating in respective direction, as you can see from the figure. So there is one common point to which both of the teeth are in contact with each other, and that point is K. From the diagram you can see that. And the direction of rotation of gear 1 is anti-clockwise, whereas gear 2 in anti-clockwise, gear 1 has a in clockwise direction. Now suppose let TT be the common tangent and N dash be the common normal to the curves at the point of common contact, point K of two mating gears, like that. This is N dash and N, and this is TT. This TT is the tangent drawn to the common point K, and this is N dash, that is the normal to that tangent T dash, which is also passed from the common point K. Along with that, also consider V1 and V2 is the velocity of a point K when considered on the gear tooth 1 and 2. That means if you are considering point K on gear teeth 1, then V1, that will be the velocity of point K whenever it is located on gear 1. And similarly, if you think that the common point K is located on gear 2, then there will be the velocity of K will be V2. So this is what about the V1 and V2. Now just you have to resolve that component of velocity V1 and V2 along the common normal N dash and N dash to N dash. So component of velocity V1 along N dash will be definitely becomes K into N dash, and that will be V1 cos alpha. Similarly, component of velocity V2 along N dash is always equal to K N dash, and it is also equal to V2 cos alpha. So over here both of the component of velocity will be always equal, having the same magnitude, so we can compare both of over here. So ultimately equation will become V1 cos alpha is equal to V2 cos alpha. Now just you have to replace V1 and V2 by putting the values of omega 1 into O1k and omega 2 into O2k. Actually this is the relation between linear velocity and angular velocity. So by putting that values and replacing V1 and V2 and convert the entire equation in terms of cos alpha, you will have the relation like O1m upon O1 into OK. Similarly, if you are considering this triangle O1m into K and adopting the similar procedure, ultimately you are finding the angle beta cos beta, and that is equal to O2n upon O2k. Now just you have to put the values of cos alpha and cos beta in previous equation, that means this equation over here, cos alpha and cos beta. you will have the equation like omega 1 into O1k into O1m upon O1k is equal to omega 2 into O2k into O2n upon O2k. Further simplification, if you are doing simplification, you will have that the O1 will be cancelled out here, so ultimately the final equation will become omega 1 into O1m is equal to omega 2 into O2n. So if you are taking the angular velocity ratio like omega 1 upon omega 2, that is equal to O2n upon O1m. Suppose if you are considering triangle O1p, O1MP and O2NP in previous slide, like this triangle, if you are taking this equation O1 and then M and P, so this is M and this is P, this triangle. And similarly you have to also consider O2 N and P, this triangle. If you are considering two triangle and applying some relation, that means mathematical simplification, then the ratio will find that by considering both of O1MP and O2NP, and in particular both of the triangle, there is a pitch point P which lies on intersection of common normal and line joining the center of gears. So both of these triangles become similar, so we can use the same relation as that of what we have already applied in case of the previous two triangles. So ultimately your triangle relationship will look like O2n upon O2p, and that is equal to O1m upon O1p. Further simplification will give us O2n upon O1m, and that is equal to O2p upon O1p. So ultimately we know that omega 1 upon omega 2, that is equal to O2n upon O1m. So this equation is by putting these values over here, so ultimately you will have the omega 1 upon omega 2, and that is equal to O2p upon O1p. This mathematical equation has some particular typical conclusion. Generally we can say that the angular velocity ratio is generally inversely proportional to the ratio of the distance of a point P from the center or gear center O1 and O2. So we can say that the angular velocity ratio largely depends on the central distance from the gear center to the point where or pitch point generally. So in order to have a constant angular velocity ratio for all the position of mating gears, the point P must be fixed point, and it is called as a pitch point. This is what about the conclusion that is derived by law of gearing. In other words, the common normal at the point of contact between a pair of teeth must be always pass through the pitch point for all the position of the mating gear. So this is the fundamental condition through which it must be satisfied while designing the profile of the gears. So this is what about known as a law of gearing, or in other words we can say that condition of correct gearing. Its law of gearing plays a very much important role whenever you are designing any gear or gear train. At that time you should to focus upon velocity ratio, and whatever the pitch point P that you are selecting should be strictly based on this law of gearing. After that, the point number 2 that we are going to discuss, that is the velocity of sliding teeth. That means suppose two gears are in constant mesh and rotating with each other and transmitting power and motion. At that time what should be the velocity of teeth which slides with each other, that we will discuss and derive the equation for that particular velocity of teeth. Now in order to have the calculation or the derivation of relation for the velocity of teeth, just you have to consider the figure that was given in previous slide. That means in case of law of gearing, particularly in that case, just focus upon the V1 and V2, and just the component of V1 and V2 should be resolved along TT. That means tangent like look at the previous slide first. ultimately just focus upon the line TT, that means this line, and you have to calculate V1, that means velocity of gear 1 and velocity of gear 2. Both of the components should be calculated based or along with this line TT. So when you considering this condition, at that time you are getting V1 along the TT is equal to V1 sin alpha, and component of velocity V2 along TT, that will be the V2 sin beta. So the velocity of sliding of surface 2 with respect to the surface 1 at the point of contact K is generally Vs is equal to V2 sin beta minus V1 sin alpha. Now once again you require to simplify that relation by putting the values of V2 into and sin beta. Similarly, in case of V1 and sin alpha, both of the values should be replaced by putting this value over here. So ultimately your equation for the sliding velocity of teeth will become omega 2 into O2 into K into Kn upon O2K minus V1 is replaced by omega 1 into O1K into sin alpha, that is replaced by Km upon O1 into K. Now further simplification, it will give us the relation like omega 2 into Kn, because O2 and O2K and O2K will be cancelled out. Similarly O1K and O1K will be also cancelled out. So ultimately your relation will remain like omega 2 into Kn minus omega 1 into Km. Now just by that law of gearing figure, just you have to put the values of Kn is equal to Kp plus Pn and Km, that is equal to Mp minus Kp. So ultimately your equation will become Vs is equal to omega 2 into Kp plus omega 2 into Pn minus omega 1 into Mp plus omega 1 into Kp. Over here just keep the values of Kp as a constant or the common. So ultimately your relation will become omega 1 plus omega 2 bracket into Kp plus omega 2 into Pn minus omega 1 into Mp. Now once again you have to consider two similar triangles that what we have already considered in case of law of gearing theory, and that two triangle is O1MP and O2NP, and from the triangles you can have the velocity, angular velocity ratio like that, omega 1 upon omega 2, that is equal to O2P upon O1P, and it can be written like Pn upon Mp. So by simplification and crossing or the multiplication with each terms, it will give the final relation like omega 1 into Mp is equal to omega 2 into Pn. Now just you have to put the values of omega 1 into Pm is equal to omega 2 into Pn over here, and make simplification because omega 2 into Pn over here, that is the positive sign, and that is the minus omega 2 into Pn. So both of the terms will be cancelled out. So ultimately the final relation for the sliding velocity will remain omega 1 plus omega 2 into Kp. So this is the sliding velocity relation, and from that relation we can see that the velocity of sliding of two meshing teeth is always proportional to the distance of the point of contact from the pitch point and the angular velocity of the two gears. So that means final equation becomes Vs is equal to we can say that omega 1 plus omega 2 into Kp. So ultimately, in short, we can say that the velocity of sliding is always equal to the product of the summation of angular velocities, that means omega 1 and omega 2, and the distance from the point of contact from the pitch point, that means Kp. Now rolling velocity, that means V suffix r, and that will be becomes r into omega 1, that is the rolling velocity. And if we are taking the ratio of velocity of sliding to velocity of rolling, then the relation holds like that, omega 1 plus omega 2 into Kp upon r into omega 1. If you are simplifying the terms, finally you will have 1 upon r bracket 1 plus omega 2 upon omega 1 into Kp. Still, if you are modifying this equation and replacing omega 2 and omega 1, then the final relation will become Vs upon Vr is equal to 1 upon R, 1 plus small t upon capital T into Kp. So this is what about the sliding velocity of any teeth which is messing with its paired gear teeth. Now after that, the third topic that we are going to discuss, that is conjugate profile, and it clear means velocity of one teeth or tooth relative to its mating teeth. Generally, if the tooth profile of a pair of gears are so designed that a constant angular velocity ratio is produced and maintained during the operation, that we actually required, that the angular velocity ratio should be constant and it should be maintained throughout the power transmission operation. And then if you are finding such a condition in particular pair of gear that the angular velocity ratio remain constant throughout the power transmission, if such a condition achieved, then we can say that the gears are said to have the conjugated action, and the tooth profiles of that gears are generally known as conjugate profiles. If tooth profiles of one gear is chosen arbitrarily, and it is possible to construct the tooth profile of the meshing gear in order to have the conjugate action when the gears are in match. So if out of two gears, one gear has a conjugate profile already given to you, so on the basis of that one gear profile that is conjugate, you can also determine, or also you can design the conjugate profile of other meshing gear too. Generally, a gear pair is said to have the conjugated profile if it satisfies the law of gearing. So prime condition is that if any gear pair have the conjugate profile, then it must be satisfied the law of gearing. Now it's time to discuss about how to draw conjugated profile. So there are basically small procedure through which you can have the drawing of conjugated profile. Generally, graphical procedure for determining the conjugate profile of one gear when profile of other gear is selected arbitrarily, it should be performed like that. Generally, look at the figure, the portion of two meshing gear 1 and 2, kindly concentrate over there, and consider the root profile of gear 1 as a 1, 2, 3, that is already you have given 1, 2, 3, 1, 2 and 3, this is the profile that you have given as input, and it is now desired to determine the profile of gear 2, which will be result in conjugated action. So 1 dash, 2 dash and 3 dash, that will be the conjugated profile that we require to have for the gear number 2. Now first step, that you have to just draw a pitch circle of both of the circle and mark the pitch point P. After that, draw the tooth profile 1, 2, 3 of gear 1, and which is already chosen arbitrarily. After that, once you are drawing the tooth profile 1, 2, 3 of gear 1, draw the tangent lines at point 1, 2 and 3 to the to profile 1, 2, 3 of gear 1. So that all that points 1, 2 and 3 from which you have to draw a tangent like that. Once you have drawn the tangent, then fourth step, draw a line perpendicular to tangent line 1 and passing through the point 1. This will intersect to pitch circle of gear 1 at point P1. Similarly, follow the procedure for point P2 and P3. So over here, suppose you are extending this tangent line, perpendicular to tangent line, it will intersect the pitch circle diameter or pitch circle. So in that way, you have to follow and draw the tangent perpendicular line to all that points 1, 2, 3 up to the pitch circle, and nominate that points P1, P2 and P3 like. Now if you have done, then kindly consider that the point K1 represents the point of contact of two gears. For constant velocity ratio, the law of gearing must be satisfied, and it follows that when the point 1 reaches to K1, the line normal at the point of contact K1 must pass through pitch point P. Therefore, P1 and P should coincide. Of course, P1 and P should be coincide, and therefore, of course, due to that procedure, point K1 can be marked on circle passing through point 1 and concentric with the pitch circle of gear 1 in such manner that the relation holds like Pk1 is equal to P1 into 1. Similarly, for point K2 and K3, you can follow the same procedure and have the relation like Pk2 is equal to P22 and Pk3 is equal to P33. After that, draw circles passing through these points K1, K2 and K3 like that. Over here, K1, draw a circle also from the point K2 and point K3. Just you have to draw these circles. After that, for getting point of contact at point K1, the point P1 has to move up to point P. That means gear 1 should turn through an angle corresponding to arc PP1 dash. That means suppose you require the point of contact at point K1, just you need to rotate gear through some angle, and so that arc P1 will be generated. So in that case, this is the P and this is the P1. So ultimately, in order to reach the P1 to P, you have to rotate your gear in some angular movement, angular displacement. Similarly, you can follow the same procedure for the gear number 2, and it must turn through the same angle so that PP1 dash we can have. So ultimately, for the gear 1 and gear 2, the arc PP1 dash, that is when you are turning gear 1, and arc PP1, that is when you are turning gear 2 through some angular displacement, both should be equal. So same procedure you can also follow for the PP2 dash and PP3 dash 2. So ultimately both of the arc, like arc PP2 dash is equal to arc PP2. And finally, once you have drawn this arc at point K1 of the gear 1 is in contact with the point 1 dash of gear 2, similarly point 2 dash and 3 dash of gear 2 are in contact with the point 2 and 3 of the gear 1 at K2 and K3 point of contact respectively. So therefore, mark 1 dash on circle which is passing through the K1 and concentric with the pitch circle of gear 2 in such a way that the P1 1 dash is equal to Pk1. And similarly, for the point 2 dash and 3 dash, you have the relation like P2 dash 2 dash is equal to Pk2 and P3 dash into 3 dash is equal to Pk3. Now finally, draw a smooth curve which pass through the points 1 dash, 2 dash and 3 dash. It will give us the conjugated profile of gear 2. That means you have to draw a smooth line which pass through this particular point 1 dash, 2 dash and 3 dash. And if you are comparing this profile with initially conjugated profile that we have already chosen as arbitrarily profile, both are nearly very similar. So by following the various steps from step 1 to step 10, you can have the conjugate profile of other meshing gear too. Now after that, it's time to discuss the various form of gear tooth profile. Generally, what we have considered that if we choose one gear tooth profile arbitrarily, then it is possible to construct the tooth profile of another meshing gear graphically, that we have discussed already in previous slide. So in order to have the conjugate action or to satisfy the law of gearing, we should to follow the graphical procedure, and on that procedure we will have the construction of conjugated profile of other meshing gear. So generally such type of gear teeth are generally known as a conjugated teeth. Now, conjugated teeth will transmit the desired motion, but even such teeth profiles are difficult to manufacture, standardize, and also the cost of production of such a profile is very much high. So, generally, conjugated tooth profile is not commonly practicable and it is not used. So, the profile of teeth which are generally widely used and also which satisfy the law of gearing have the two common form, that is one is like cycloidal profile of teeth and other one is involute profile of teeth. Now starting with the cycloidal profile, basically a cycloid is a curve which is traced by a point on the circumference of a circle which rolls without slipping on a fixed straight line. Generally, cycloid profile or the cycloid is basically a curve, and if you are for example, look at the figure number A. There is one cylinder which is given to you, and if you are rolling that cylinder and tracing the path that will be traced by this particular point P after some angular displacement of that cylinder, you will have the cycloidal profile like that. So this is how the cycloidal profile is possible to generate. Suppose if the circle rolls without slipping outside the base circle, the curve traced by the point on the circumference is epicycloid. And if circle rolls without the slipping inside the base circle, so whatever the curve traced by a point on the circumference is called as a hypocycloid. So over here you can see that this is the hypocycloid. This is produced because the whatever the circle we are rolling, which is inside that outer circle or base circle. So in that case, whatever the profile that you are generating, that will be the hypocycloid. But if you are rolling circle without slipping to outside that base circle or fixed line, that will be a we can say that the epicycloid will be generated like that. Over here, look at this is the epicycloid profile, and this circle is rolling without slipping inside that particular we can say that the base circle. So this is what the difference between we can say that epicycloid and hypocycloid. Now when circle C rolls without slipping above the pitch circle in the direction you can see from the figure, then the point P on the circle trace generally epicycloid PA, and this represents the face of the cycloid tooth. So look at the diagram, you will have the PA, so this is face, and of course we have discussed in my previous video lecture during terminology of the gear tooth, in which generally we know that the face is the top surface above the pitch circle. So whenever you are doing so for generating the profile, cycloid profile, whatever the surface or the profile or curve generated above the we can say that the pitch circle diameter, it will be generally known as a surface, or we can say that the top surface. Now when a circle D rolls without slipping below the pitch circle, that means if you are rolling this circle D without slipping and inside that base circle or pitch circle, that means this is the pitch circle and you are rolling this circle inside it. So once again there will be of course the profile will be generated, and this will be known as a PB profile. This PB profile exactly represents the flank of cycloidal tooth profile. Now if you are joining entire profile like APB, then it will be nothing other than the cycloidal profile. So this is what about how the cycloidal profile can be possible to generate by gear or the gear wheels. After that there is a second types of gear teeth profile, that is an involute profile. Basically involute is also a type of curve generally which is generated by the end point of a cord which is unwound over the circle. This is the end point of circle and which is unwound whenever the circle is going to be rotated. So in that way if you are doing so and you are creating profile, of course the profile so generated will be known as an involute profile. Now consider figure top left hand side figure. You have given one string which is initially wrapped around the circle, and that circle is fixed end point, attached to the circle at point F, and its free end point P coincide with the point A on the circle. So over here look at this diagram. You have given one circle and a string is wrapped around. Free end is over here. One at the free end there is a point P2, and initial point free end of this string is exactly on the outer periphery of that particular rod. Now when string is unwrapped into the point A1, and then the free end will trace the curve PP1. Now what you have to do, just you have to unwrap the string that has been wounded already to point A1 like that. So this end will be separate out from the winding position of the outer peripheral surface of the gear wheel or simply circle. So it represents basically A1 and P1. Still you are unwrapping the string to point A2, so ultimately you are getting the chord length, free chord length A2P2. On that similar manner, if you are unwrapping the remaining portion of that string, then it will give like the profile of in that manner. And if you are joining by so, you will have the one profile, and that profile that will be the involute curve. So according to the free end of string, it will generate the involute curve as it unwraps progressively from the circle. Ultimately in that way, if you are unwrapping the string that is already wounded on the outer surface of the circle, and you are continuously unwrapping, so in that way you are generating the profile from point P1 to P2, P3, P4 to up to Pn. Now just consider the below exactly figure given to it. Two gear blanks with fixed center O1 and O2, and which radius is also given, and that radius is O1A and O2B that you have given. Now consider a string having its end attached to two gear blanks at point A and B. Now point P represents a fixed point on the string through which a pencil point is projects out. Now if gear blank 2 is fixed and gear 1 is free to rotate, then the point T on the string is moved around and about gear blank 2 in anti-clockwise direction. So it will generate an involute curve TE like that. This is T and this will be the E. So if you are following this procedure, you will have the profile of T. Similarly, if you are performing reverse to that of the procedure, if gear blank 1 is now fixed and gear blank 2 is free to rotate, then point T on the string will generate the involute curve TD. So over here there is a T and this curve. If you are fixing the gear 1 and gear 2 is free to rotate, you will have the tooth profile like that. Now if chord is replaced by two plates having involute shapes which are fixed to the respective base cylinder as shown in the figure you have given, the path of contact will be on the line AB, and which corresponds to the string of earlier case. Now line AB is normal to both the profiles at all the points of contact, and therefore motion of point T is always normal to corresponding radius of rotation of BT and AT. So as long as the center distance remains same, the common tangent to base circle remain in the same position, and it cuts the line joining of center O1 and O2 always at the pitch point P, and this shows that the involute tooth profile also satisfies the law of gearing. So this is what about the involute gear. Dear student, this entire lecture I have discussed upon law of gearing, then after velocity of sliding, and at the end we have detailing about the types of forms of gear like involute and cycloid. Thank you very much for your kind of attendance. If you have any question, let me inform, let me ask, we will have the solution. Thank you very much.